Hello, we're going to talk about distance, rate, and time today. This is one of the most fundamental concepts when it comes to word problems. The fact that distance is equal to rate times time. We dealt with this a little bit when we started dimensional analysis. We canceled units. I don't know if you remember back when we did the ratio, and we had problems like take 6 days and change it over into weeks. How many weeks is that? And we could say 6 days times 1 day, 7 days for 1 week. And we would cancel out the word days by putting the 6 days over 1. And we know that that's 6/7. Now, this wasn't the most complicated example, but it's an idea of what we're doing here. Distance is equal to rate times time. Probably more appropriately is that, I don't know why I'm erasing that, is that distance divided by time is equal to rate. Or in other words, I'm going to write this over here, a rate is equal to a change in distance over a change in time. An example of that, probably a more common one, is miles per hour. How many miles can you travel in 1 hour? I think many of you have seen the YouTube video where the girl is trying to explain how far you can go in 1 hour if you're going 60 miles an hour and those kind of things. Those are actually distance, rate, time problems more so than anything. So we're going to look at some problems here, and I'm actually going to start with number 1, and then we're going to go back up and start to work on this chart a little bit. So I'm going to skip around a little bit. But I want you to sort of have an idea of a visual in your head. Mary Beth and Michael leave school traveling in opposite directions. So if this is our little school, and there's a school. Mary goes one way, Mary Beth. Michael goes another. It says Michael is walking and Mary Beth is biking. So I'm actually going to draw Mary Beth going a little bit further. Say that this is Michael and this is Mary Beth. Mary Beth is biking, averaging 6 kilometers per hour more than Michael. If they are 18 kilometers apart after 1.5 hours, what is the rate of each? Don't forget units. Okay. When I say don't forget units, I mean don't forget units. I mean put units down. I mean they must be present somewhere either in the chart or whatever. Do not forget units at all in any problem that we're doing for the next 2 weeks. Units are crucial. Let statements are crucial if you don't use a table. So we're going to kind of do this with a table, and I'm going to set up my table as rate times time equals distance. Rate times time equals distance. The rate here, well, we have 2 rows. We want Mary Beth and Michael, so I'm going to put Mary Beth here, and I'm going to put Michael here. Michael is walking, Mary Beth is biking. Mary Beth is biking 6 kilometers per hour more than Michael. So Michael's rate, let's call that x. And just for the purposes of this, I'm going to say let x equal Michael's rate. Units need to be present, so we're going to say in kilometers per hour. And if you don't put a let statement, we need to put rate up here, kilometers per hour. That means that our time should be in hours and our distance should be in kilometers because those have to match. Think about the units. If I have kilometers per hour times hours, that's going to be equal to kilometers. Rate times time is equal to distance. Mary Beth averages 6 kilometers per hour more, so Mary Beth's rate is x plus 6. If they are 1.8 kilometers apart after 1.5 hours, what is the rate of each? Well, Mary Beth biked for 1.5 hours, and so did Michael. Michael biked for 1.5 hours. It's okay to use decimals here, which is solving a problem. It says they're 18 kilometers apart. This is kind of a crucial thing here because that represents a total distance. So I'm going to sort of flop back up to the chart at the top here and say that we have three types of distance relationships, this is motion in an opposite direction. Example number 1. One person going this way from a starting point, one person is going this way. And the idea with opposite direction is that you have distance 1 plus distance 2 equals a total distance. So most of the time you leave at the same time, so we're actually talking about the same time here. As you can see from this, the time was the same. But if we talk about distance, okay, let's go back. We're going to have, a total distance on the whole thing. So my total distance, I'm going to add a little thing here, should be the 18 kilometers from the problem. Then I can do rate times time, 1.5x plus 1.5 times 6 would be 9. And then I have 1.5x here, and that's going to be my problem. 1.5x plus 9 plus 1.5x is equal to 18. 3x plus 9 equals 18. Subtract 9 from both sides, you get 3x is equal to 9. X is equal to 3. And then we have to go back to say, what is the problem actually asking? It's asking for the rate of each. So, Mary Beth bikes at 9 miles, or kilometers, not miles. How'd I get 9? Well, 3 plus 6. And Michael walks at 3 kilometers per hour. Does our answer make sense? Sure. Mary Beth should be biking a lot more than Michael is walking. Okay, let's skip on down to number 2. We have Carla begins biking south. Dean leaves from the same point to catch up to her. So this is a little bit of a different problem. If I could say Carla, I'm going to draw a little representation of a starting point for Carla, and she begins biking south, going 20 kilometers per hour. Dean leaves from the same point 15 minutes later. Here's Dean. Now this graph doesn't represent time, but it represents where they left, so I'm just kind of doing a little sketch here. Dean bikes at 24 kilometers per hour. How long does it take before they catch up? So this isn't a case of total distance. This is actually a case of we have the same distance going on. So I'm going to take this and I'm going to put this back up at the top here. We have motion in the same direction. I'm going to sort of do this here where we kind of leave and another person leaves. Maybe time is different. So I'm going to put maybe time is different because it was in this problem. But the idea is that we have the same distance covered in both. If we start from the same point and end at the same point, distance 1 equals distance 2. Let's go back down to here. Let's start filling in our chart. We have Carla and Dean. Rate in kilometers per hour times time in hours. Let's make that just an H. Equals distance in kilometers. Rate times time equals distance. What is Carla's rate? Carla begins biking south at 12 kilometers per hour, or 20 kilometers per hour. Dean leaves from the same point 15 minutes later to catch up with her. Dean bikes at 24 kilometers per hour. How long? The question is time. So let's say it says how long will it take him to catch up to Carla. The question is specifically Dean's time. So I'm going to make Dean's time be the variable, and I'm actually going to use t instead of x just to kind of make it a little bit more, specific. Okay, Carla left 15 minutes earlier. Dean left 15 minutes later. If I leave 15 minutes before someone else does, I'm actually traveling for more time. And that is kind of crucial here. I want you to look at this and see why this is going to be t plus a certain amount of time. Think about the balance here. I'm going to use like a little scale and kind of draw this out. Carla's scale has her going at 20 kilometers per hour. whereas Dean has him going at 24. Since Dean's rate is bigger, his time must be smaller. We're going to stick him with the t, and we're going to stick Carla with the t plus. And here's the other catch. This is going to be t plus 1/4. I'm going to write that here too. So less time, bigger rate, more time, less rate. Now why is it t plus 1/4? Because 15 minutes is 1/4 of an hour, and our units are in hours. Yep, you're going to have to be careful about a lot of things here. That's a big one, and keeping the balance here is the big one too. The fact that if Carla leaves earlier, she's actually traveling more time. You would think leaving earlier would be minus, but it's not. She travels more time. Furthermore, we do rate times time, so I'm going to get distance is 20t plus 1/4 of 20 is 5. And then we have 24t. It's like, how do we relate these two? Remember, if we looked at what's going on here, it's actually a same distance. The distance was the same. When things are the same, we stick an equal sign between them to show that. So I have negative 4t is equal to negative 5, or t is equal to 5/4. 5/4 is 1 1/4. How long will it take him to catch up? It takes 1 hour and 15 minutes. Let's go down to the next one. Mark drove his car to the garage at 48 kilometers per hour and walked back home at 8 kilometers per hour. The drive took 10 minutes less than the walk home. How far did Mark walk and for how long? Well, we got a bunch of stuff going on here, but we still have a rate in kilometers per hour, a time in hours, and a distance in kilometers. Rate times time equals distance. Mark drove his car to the garage and then back home. We'll call this the walk home. So there's two trips going on, but it's the same person. This is what we call the round trip. And if we look back up, round trips are, I go this way, then I go this way. We have another case of distance 1 equaling distance 2. So it's the same distance situation. Let's go back down here. Mark drove his car at 48, walked home at 8 kilometers per hour. The drive took 10 minutes less than the walk home. So if the walk home was a certain amount rate, let's say the walk home was t, the drive was t minus 1/6, because we expect the drive to be less. And the distance would be 48 minus 8, sorry, 48t minus 8, and then 8t. And we know those two have to be equal to each other. 48t minus 8 is equal to 8t. 48t minus 8 is equal to 8t. Subtract 8t, and I get 40t is equal to, add 8, get 8. So t is equal to 1/5. 1/5 of an hour, well, we know what that is. That's 12 minutes, but let's get down to what the question's asking. It wants to know, if I can be allowed to sneak a highlight in. Come on. Yes, you can. It wants to know what this is. It wants to know how far did Mark walk and for how long. So it does want to know the t part. So we didn't completely waste our time in figuring out what the t is. We just had to apply it. Let's keep those on so I can change colors later. Alright, back to the problem. Mark walked for, we said 1/5 of an hour is 12 minutes. And let's do 1/5 times 8. So 8 times 1/5 is 8/5. 8/5 kilometers. We can change that into a decimal because really what we want to do is express this in things that people would know. So that's 1 3/5. 1 3/5 is Mark walked for 12 minutes, 1.6 kilometers. By the way, 1.6 kilometers is about a mile. 12-minute mile walk is a pretty rapid walk. Okay. Mrs. Pomeroy takes her Sunday drive into the country at an average rate of 60 kilometers per hour. Yes, we are in Canada right now. 60 kilometers per hour. She returns over the same road at an average rate of 48 kilometers per hour. We have another round trip, so I can say into the country for trip 1, and then we'll say the return, maybe for trip 2. I have a rate in kilometers per hour. I have time in hours, distance in kilometers, rate times time equals distance. The rate into the country is 60, the return is 48. The round trip takes 3 hours. Ooh, we have a total time. So I'm going to create a 3 here. How many kilometers does she travel altogether? Very easy way to do this. One thing I know we can do is say, let's just let t be the into the country, and then the other part would have to be the total minus the t. So 3 minus t. I could have actually reversed those. Doesn't matter. As long as you pick one and you stick with it. Because we know when we do a round trip, our distances are the same. So 60t, and then this one's going to be 3 times 48 is 3 times 50, but then minus 6, so 144 minus 48t. And I know 60t is equal to 144 minus 48t. Add 48 to both sides, I get 108t is equal to 144. Or t is equal to, this is going to be 144 over 108. Let's see if we can do this without a calculator. Divide by 9, I get 1 and 6. Divide by 9, I get 1 and 2. Divide by 4, and I get 4, then over 3. So 1 1/3 hours. It wants to know how many kilometers she travels altogether. So really, again, what it wants to know is this thing, the distance. Technically, it wants to know the total distance, but let's just find the into the country and then double it. Strictly speaking, I should be able to take this and plug it into here or here. It should be the same thing because the two sides were equal to each other. Regardless, I think it's easier to do 60 times 40 times 4/3. 60 divided by 3 is 20. 20 times 4 is 80. So we have 80 for a single trip, double 80, and she traveled 160 kilometers. Again, I should be able to take that and plug it into here too. Do 144 minus 48 times 4/3. 4/3 of 48 is, well, 48 divided by 3 is 1 and 16. 16 times 4 is 64, so it's 144 minus 64, which is 80. So again, those two matched, which they should. Just double them and you get the 160, which is the total trip. Finally, if you want to put fear into your parents, just start any sentence with 2 trains. So they'll freak out. 2 trains, train 1 and true, leave the station at the same time, traveling in opposite directions. Way back up to the top, we have motion in opposite direction. We have a total distance situation. Go back all the way to the bottom. We have train number 1 and train number 2. After 5 hours, they are 595 miles apart. Let's fill in the rate, time, distance thing. Rate, I see miles, I see hours. This is going to be miles per hour. Time then will be in hours. And distance is going to be in miles. It's really best practice to avoid putting like M for miles because that should be meters. You can do MI for miles or just spell it out. Unless you do MPH. Okay, I guess that's confusing. Just, make it look good. Okay, let's read it again. Leave a station at the same time, traveling in opposite directions. After 5 hours, they are 595 miles apart. You should be able to pick apart this sentence and start putting some things where it should be. For example, I should be able to pick apart that sentence and say, this train traveled for 5 hours and this train traveled for 5 hours, and they are 595 miles apart. That's a total distance. train 1 traveled at a constant rate going west, and train 2 traveled 15 miles per hour faster than train 1 going east. But train 1's rate is r. Train 2's rate would be r plus 15. How fast was each train going? Well, let's multiply 5r, then 5r plus, that would be 75. Do an equation from this. 5r plus 75 is equal to 595. That would be 10r. If I subtracted the 75, I'd get 520, and I have r is equal to 52. Train number 1 was going 52 miles per hour. And train number 2 was going, well, r plus 15, so 67 miles per hour.